This talk's going to be about some joint work with my advisor, Daniel Greer, who's also at UC San Diego. And yeah, the title of the talk is Quantum Threshold is Powerful. And so that might not be too revealing as to what the topic is, because some people talk about these thresholds in error correction, but no, that is not the threshold we're going to be talking about today. This is going to be a talk about circuit complexity. And so I'll just get started. Oh, but I guess before I get started, I'll say a brief outline of the talk is that I'm going to sort of go through sort of a crash course, I guess, in the first part on classical circuit complexity, some of the highlights and big results there. And then in the second part of the talk, I'll get more into our sort of purely quantum results and some of the challenges, I guess, in history associated with I guess the study of quantum circuit complexity. So yeah, so I guess I'll get started now. So yes, throughout this talk, I guess the sort of motivating question to keep in mind is what is the power of a large multi-qubit gate, sort of in a generic quantum circuit. And so in particular, the setting that I'll be sort of assuming for the rest of the talk with our quantum circuits is that we have the ability to implement arbitrary 1 and 2 qubit gates sort of for free, and then at some cost, we'll be able to implement some restricted set of multi-qubit gates. And this will sort of count toward the cost of our circuit. Later, we'll see this as the size of the circuit. Okay, so 1 and 2 qubit gates here, we have some examples, the Hadamard and the CNOT that we all know and love, but here we're assuming that also you're allowed to have arbitrary rotations on a single qubit of sort of any angle. So there's no assumptions on which 1 and 2 qubit unitaries you can implement there. So just arbitrary sort of 2x2 and 4x4 unitaries. And then, yeah, sort of this restricted set of multi-qubit gates that I was referring to is going to remain a bit vague for now. But maybe one example you might think of is the unitary displayed on the right here, which acts on, say, n+1 qubits, and sort of in superposition computes the parity of these n qubits, these first n qubits, and then sort of XORs the result into this final register. And so you can see that sort of decomposed here as a sequence of n CNOT gates, each controlled on these like sort of input wires and then output onto this like final wire, which I'll sometimes refer to as like an output wire. Yeah, so sort of this like naive like linear depth decomposition is sort of only for demonstration purposes. Like in this setting that I'm describing, we're assuming that like you can implement this gate sort of in depth 1. And that's all it counts for. Like we don't need to worry about this sort of naive decomposition we have on the right hand side. Yeah, so the first sort of observation one might make in this setting is that if you have some large n qubit unitary, then there is a method of decomposing it efficiently into 1 and 2 qubit gates. So for example, this can be done with like the Solovey-Kitaev theorem and sort of with Solovey-Kitaev type methods for decomposing unitaries into 1 and 2 qubit gates. And I won't get too much into that, but I'll sort of describe how this is done with this unitary that I just mentioned. Oh, I guess I should mention this. The name of this unitary is sort of the parity gates or the parity unitary. And so I just mentioned that for demonstration purposes and maybe most easy to think about is this sort of naive way of decomposing it into a sequence of n CNOT gates sort of applied one after the other. Yeah, this results in depth exactly n, and the number of gates you use is exactly n. But it turns out there's sort of a slightly more clever way you can do this, whereby you sort of alternate in sort of this like binary tree sort of fashion, still with CNOT gates, still with n C0 gates, but the resulting circuit is only going to have a depth log n. And I guess I'll mention what I mean here and throughout the talk by depth is that this is the number of layers of multi-qubit gates in the final circuit that we have. Yeah, and so here you can sort of maybe see from this depiction that there's this sort of binary search type method by which you can sort of implement the same unitary, but you get this like log depth rather than linear, which is what you might achieve sort of naively.
Sorry to interrupt you. So when you say that this is large entangling gates, so these gates do produce the absolutely maximally entangled state, or in general you are saying that large entangling gates?
Yeah. So no. So here, I guess what I mean by large entangling gates is just some unitary that acts on a large number of qubits, and let's say results in pairwise entanglement between every two pairs of qubits. Yeah. That's all I mean by that.
Got it. Thanks.
Yeah, good question. Okay, so I'll return to our sort of motivating question here about like what is the power of large multi-qubit gates by adding like another restriction. What is the power of large multi-qubit gates in constant depth? So by this thing I just mentioned about the Solovay-Kitaev theorem, if you're familiar, is that you can always decompose any unitary into some sort of product of 1 and 2 qubit unitaries, possibly using ancilla. And so it might seem that having sort of these like globally entangling gates doesn't really bias anything because we have sort of these like efficient methods of decomposing into 1 and 2 qubit gates. But now I'll add this restriction that we would like for the resulting circuit to have some low depth. And in particular, we're going to focus on circuits where the depth is constant, meaning that it's sort of doesn't depend on the input size. It's some fixed constant. And so sort of one practical motivation for this is that focusing on constant depth circuits is sort of in line with sort of this near-term intermediate scale quantum machines that perhaps you all have heard something about, is that we don't want to have very deep quantum circuits doing our computations because this will allow for more time for the qubits to decohere. And moreover, if somehow we could get away with implementing one of these large multi-qubit gates with like the same or better fidelity than we could with our 1 and 2 qubit gates, then somehow having less gates in our circuit allows for less sort of infidelities or to accumulate, less errors to accumulate. And so perhaps constant depth is the sort of desirable thing to have there. And is there a question?
Yeah. So I was just thinking, maybe so when you say that in experiments there is possibility for less decoherence, and the large gates fidelity might be better in the fidelity of the circuit. So when you say fidelity, it means there is the static error is less or more in case of large multi-qubit gates, or a sequence of smaller gates, other than decoherence.
Yeah. So I'm not an experimentalist, so this claim is not meant to be absolute or anything. But I think the sort of idea that I'm getting at here is that like imagine we could have some n qubit gate that had like the same or better fidelity than just a one or 2 qubit gate. Yeah. Then if we could take advantage of this in low depth, then it would be better than just like not naively, but Solovay-Kitaev type decomposition for our circuit into 1 and 2 qubit gates. Yeah. That's all I mean by better fidelity there.
Sure.
Which is perhaps not well practically motivated, but I suppose it's a consideration. I think in particular for like neutral atom array type quantum computers, they are actually able to implement these sort of like very large entangling gates on like a large number of qubits at once with fidelity that's like comparable to their 1 and 2 qubit fidelities.
Okay.
Yeah.
Sure.
And then one other motivation for this sort of constant depth restriction is that we have sort of a long line of works in recent years I guess as well as going back to Terhol and DiVincenzo, in which it's been shown that constant depth quantum computers, some restricted models of constant depth circuits are actually able to perform tasks that we can prove are impossible classically. So in particular, the result I'm talking about here is this paper of Ravi Gossin and Koenig, in which they show that a constant depth quantum circuit is able to perform some task, solve some computational problem, which we can prove that sort of the analogous classical model cannot do. And so usually these sort of impossibility results are sort of out of sight. These sort of like unconditional quantum advantage results are sort of out of sight because this would, require saying something that would be sort of groundbreaking in both classical and quantum complexity theory. But when you restrict to these sort of very low depth and restricted models, as is the case in this Ravi Gossin and Koenig result, then it turns out you actually are able to prove things. So these models are very maybe not realistic, but we are able to unconditionally show that constant depth quantum computers can indeed do something that the constant depth classical circuits can't. And then sort of along the same lines is this very classic results of Terhol and DiVincenzo, in which they show that if you did have an algorithm which was able to efficiently sample exactly from the same distribution as one produced by a constant depth quantum circuit, then something very unlikely would happen in classical complexity theory, which is that the polynomial hierarchy would collapse. So this result isn't unconditional, but it's sort of maybe the next best thing is we have strong reasons to believe that the polynomial hierarchy won't collapse, and so so this is like a very weak conditional. It's a very plausible complexity theoretic conjecture. And moreover, sort of these low depth circuit models, these constant depth circuit models, are very well studied in the classical literature. And so this was sort of a mainline thing in complexity theory in the later half of the 20th century, and even until today, is we're able to prove some very strong things about these sort of constant depth classical circuit classes. And so that's another good reason to restrict our attention. And so let me refine this question even more, sort of in light of the points that I just brought up, which is what classical circuit results, what do we know about classical circuits that could possibly carry over into the quantum setting? And so let me sort of make this formal now. What I mean by a classical circuit is just some Boolean circuit, sort of consisting of, let's say, like and, or, and not gates, which takes in our input bits, x1 through xn here, and produces a single output bit, either a 0 or 1, and we say that this circuit computes some Boolean function f, which sort of just corresponds to the inputs and outputs. And in the quantum setting, we sort of cannot exactly define something that does this because, of course, our quantum circuit needs to be reversible. And so we have this definition that I'm sure most of us are familiar with, which is that we say our quantum circuit computes a Boolean function f if it is able to implement a unitary that sort of acts like this, wherein we have our sort of input qubits, x1 through xn, and after sort of applying this circuit, the result is that the last sort of output qubit is flipped according to the value of this function f. And that's sort of the definition we'll go with, and that should hopefully be familiar for what it means to compute a Boolean function with a quantum circuit. Okay, and so one example we have here is this parity function, whose unitary I described earlier, but in case anyone's unfamiliar, this is just the Boolean function that corresponds to taking all of the input bits and looking at whether the resulting sum is even or odd. So just the sum of xi mod 2. And then on the right here, you can see, if our quantum circuit acts like this, then we say it's computing the parity function. And I have a red asterisk here, which I'll return to later, but there is sort of an interesting subtlety here doesn't allow for these definitions to be like totally analogous. But I'll return to that later. Okay, and so yeah, earlier we asked like which classical circuit complexity results hold in this quantum setting. And so to make this question precise, let's suppose we have two classical circuit complexity classes, C1 and C2. And we know that C1 is strictly contained in C2. When is it the case that a quantum analog of C1 is strictly contained in a quantum analog of C2? And so, yeah, this is sort of the perspective that I'll take for the next part of the talk. When can our
Jack?
Yeah.
Sorry to interrupt. There's a question. Uttam, do you want to ask?
Yeah. So I just want to clarify before we proceed, right? So in Bravi-Gossett conic paper, the problem was search problem there.
Yeah.
So are you going to like do the search problem for your talk, or you will be considering decision problems? Because the functions that you are taking are like decision problems.
Yeah, no, that's a good question. Yeah, for this talk, we'll be focusing on decision problems. Yeah, the Bravi-Gossett and Koenig result is about a search problem. And in fact, you can show that if you wanted to like upgrade that result to a decision problem, which could be decided by a quantum circuit, but not by a classical one, then in fact this is like provably false. These sort of classes that they consider are equivalent for decision problems.
Oh, I see.
Yeah, that's the Litecoin argument, right?
Yeah, exactly.
Okay, thank you.
Sure.
Yeah, and here that doesn't apply because you're applying these multi-qubit gates, I guess.
Yes, exactly. Yeah. So we'll get to that shortly. Yeah. Okay. Yeah. So right. So yeah, I guess yeah, that question should make me say that these classical classes here are specifically decision classes, and so for the next few slides, I guess for the rest of the talk, we will only be talking about decision problems. Yeah. Okay, so sort of here's a toy example of sort of a classical result that we know to be true. And so yeah, let's just like briefly walk through what this string of characters means. So NC0 on the left here is strictly contained in NC02. So let me define NC0. NC0 is the class of decision problems which can be decided by a constant depth circuit where all of the gates have some bounded fan-in, meaning the number of ingoing wires to any gate is bounded by a constant. And for simplicity, let's just take it to be 2 here. And so on the right here, you can see that every single gate only has 2 inputs going into it. Yeah, as I mentioned, the 0 in the superscript just means that the depth of the circuit should not scale with the input size. It should be some fixed constant. Yeah, this class actually stands for Nick's class, but you can just imagine that it means no large gates. Every gate has some fixed fan-in. And NC02 on the right here just means that we're going to augment this class, sort of in the way that I described earlier, with this additional ability to compute parity. So now we're having bounded fan-in and an OR gate, as well as parity gates of any fan-in in our circuit. And so you can ask, okay, which what is the decision problem that's in NC02 but not in NC0? And the answer is parity. Okay, yeah, sorry, went a little bit out of order there, but yeah, let me talk about how to prove things about NC0. And so, as someone mentioned earlier, we have this sort of trick called this light cone method. What is this light cone method? Okay, let's suppose on the right here we have our NC0 circuit, and it's computing some Boolean function f, and this sort of highlighted wire here where the arrow is going to be the output bit of our circuit. And so what one can do is sort of inspect the gates that could have possibly affected the output bit on this output wire. And so if you trace back, you get to this gate here, which has 2 incoming wires, and this leads us to 2 more gates that both have 2 more incoming wires. And so the point is, as you go back further and further, every time you hit a gate, the number of incoming wires, or the number of bits that could possibly affect what gets put on this output wire, doubles. But this is okay, because the depth of our circuit is some constant, which means that the total number of bits that could have possibly affected this output bit is bounded by some constant. In particular, it's bounded by this 2 to the d on the left here, and d, remember, is a constant. And so we call this the backward light cone of this output bit, meaning maybe inspired by some physics language, is the set of all possible input bits that could possibly affect this output bit. And so the point I was just making is that the size of this backwards light cone, the total number of input bits that could have possibly affected this output bit, is bounded by some constant. Now, okay, I mentioned earlier that this parity function is the function that is computable by NC02, but is not computable by NC0. And sort of the way to see this is by looking at light cones. On the right, we have our NC0 circuit. And if it were able to compute parity, then it should be the case that the size of this output bit's light cone sort of is all of the input bits. And so the reason for this is that the parity function is sort of this like maximally sensitive Boolean function. And by that I mean, if you were to flip a single, so if we fixed all the input bits, this x1 through xn here, and then flipped a single bit, the result of the parity function would flip. Remember, because it just checks what the, whether or not the number of input bits set to 1 is even or odd. Right. So flipping every single bit is going to result in a change in the value of this function. But this is a problem for our NC0 circuit, because as I just described, you can sort of use this light cone trick to bound the size of the set of input bits which could possibly affect the output. And since this is a constant, this is sort of in conflict with the parity function, where all n input bits could affect the output. And in particular, this implies that parity is not in NC0. But we do know that it is in NC02, because you could have an NC02 circuit that just consists of a single parity gate, and this correctly computes the parity function.
Can I ask a silly question? So it sounds like even if you have a function, a Boolean function that is super constant sensitive, that should also not be in NC0, right? By the same argument.
Yeah, exactly.
And do we know that necessarily means that it's in NC02? Like any super constant Boolean function is in NC02? Probably not, right?
No, yeah, so that's a good question. This sort of NC02 class is a bit unnatural. Like I don't know if anyone actually has cared to study this class, but I'm pretty sure it's not too hard to show that, like, for example, the AND function isn't computable in NC02. Yeah, I think you might be able to prove this using like just polynomials over F2, and yeah, something like that.
Makes sense. Okay.
Any more questions before we move on?
Sorry. Sorry, there were two of us. Can I go ahead?
Sure, yeah.
Sure. So can you just remind me what is the definition of NC02?
Yeah, so NC02 is just NC0, meaning that the gates in your circuit need to be bounded fan-in and in OR gates, and you can also have NOT gates. But the 2 just means that you can have a parity gate anywhere in your circuit, and this parity gate can act on any number of bits. Does this make sense?
Sorry, I was muted. I was asking if the parity can act on growing number of bits or constant number of bits. The fanning of.
Yeah, so the parity gates here can act on any number of bits. So like up like n or even more. Yeah.
Oh, okay. Okay.
Yeah. So I had a doubt about the sensitivity part. So isn't sensitivity of parity as well like 1? It's not a super constant sensitivity, right?
Oh yeah, maybe I was like not being careful with my language earlier. All I meant to say is that parity is sensitive to all input bits. Yeah, at the moment I can't think of like what that quantitatively would yield as the sensitivity of parity. But yeah, probably 1. Yeah, all I meant to say by that is that parity flipping any bit will result in the function's value changing.
So that's what I
Right.
also meant actually. Sorry. Yeah.
Okay. Cool.
Sorry. In
Okay,
that case, can you remind one more question, follow up on that? What is it? What do you mean by sensitivity of parity? What is the definition of sensitivity?
I won't define sensitivity, but I think the sort of only thing I'm trying to get at here is that like parity is a function that like very strongly depends on all of the input bits.
Right. I agree with you. So the definition of sensitivity in Boolean function that I am aware of is the number of neighbors which take different value than yourself. Right?
Yeah.
So for the parity, it will be n. That every point, actually, if parity is defined on n bits, then all points you are sensitive, all neighbors you are sensitive on.
Right. Yeah, you can think of parity as like sort of like a coloring of the Boolean hypercube.
Right.
And all of your yeah.
So,
But I can't recall
then the sensitivity of parity is n, not 1, right? Sorry, I just got mixed up in this last thing that you were discussing.
Yeah, I suppose maybe there's like a normalizing factor or something, but I can't recall like the quantitative definition of sensitivity at the moment.
Sure.
But
Yeah.
This will not be super important. Yeah. Okay, I think I'll move on here. Right. Okay. So this whole discussion of NC0 and NC02, this is a classical result that we like know how to prove with not too much trouble, sort of using this light cone method that I just described. And so you might be tempted to ask, does the quantum analog of this result hold? Absolutely. And it turns out that yes, it does. But before I explain why, let me just define these classes properly. Right, so QNC0 is going to be very much analogous to the way that NC0 was defined, except, instead of and OR gates now, we're going to allow for any 1 and 2 qubit gates to be present in the circuit. So any gates that act on at most 2 qubits are allowed in our QNC0 circuit. And again, the 0 in the superscript means that the depth of the circuit still needs to be constant and not growing with the input size. I guess the first thing I'll mention is that you can still sort of apply this light cone trick that I just described in basically the same way. So every time, so let's focus on this wire here with this arrow to the right. Every time you encounter a 2 qubit gate that's acting on this output wire, you can just grow the size of the light cone. You can now include this new wire in this set that will eventually become the light cone. And for exactly the same reason as before, the size of this backwards light cone will always remain a constant, because in every layer it at most doubles, and the depth of the circuit is constant. Okay, and now let me define QNC02. QNC02 is this circuit class that we get when we allow for sort of any 1 and 2 qubit gates and this parity unitary to be applied anywhere in the circuit. So this is this n plus 1 qubit unitary, which acts sort of as defined on the left. It computes this parity function in superposition. And so it shouldn't be too hard to see that sort of the classical result that we just went through also holds for these quantum analogs that we've defined. Namely because the circuit on the left, or sort of the definition of parity there, that is a QNC02 circuit. Whereas on the right here, we've highlighted this light cone which corresponds to all of the input bits, which could possibly affect this output bit. And so for sort of the same reasons that we were just discussing, QNC0 cannot compute this parity function. And I think I mentioned this earlier in the talk, is that QNC0 can actually only compute the same Boolean functions that NC0 can, like precisely for this light cone reason. Okay, any questions? Okay, I'll move on then. Okay, now let's upgrade our circuit class a little bit. This NC0 class and this NC02 class we were discussing are like very weak in some sense. So now let's talk about AC0, which is sort of the next weakest model of circuits you could hope to define. And so the sort of result we have here in classical circuit land is AC0 is strictly contained in AC02. And this was first proved by Aitai, first Sachs and Sipser in 1983. And so let me define this AC0 class. So it's going to be sort of the same as NC0 in that AND and OR gates are all you get. But now it's going to be allowed for the circuit to have unbounded fan-in, or sorry, for the gates to have unbounded fan-in, meaning that your AND and OR gates can actually take any number of bits as input. And so previously in NC0, it was only the case that your AND and OR gates could have 2 input bits, or some fixed constant number of bits feeding in. But now we're going to lift that restriction and say, okay, AND and OR gates can have any number of incoming bits. And again, the 0 in the superscript denotes constant depth. And so this sort of light cone trick from before won't work anymore. So sort of the fact that we were sort of basing that whole discussion on was that the gates in the circuit only had fan-in 2. But now the fan-in can be, anything, which means that the light cone could actually grow to include every single bit that the circuit is taking as input. So this light cone trick from before is just not going to work. Let me just mention AC02, sort of in analogy with the classes defined so far, is what we get when we take AC0 and augment it with the ability to compute this parity function on any number of bits anywhere in the circuit. And so you might wonder, okay, if this light cone trick fails, is there anything else we could possibly hope to do to show that AC0 can't compute some Boolean function? And there is sort of this very beautiful and magical method of random restrictions, which maybe you've heard of. I won't get into this too deeply, but the general idea is that you sort of randomly pick some bits to fix your inputs. So you randomly sample some bits to fix your inputs as some subset of your inputs, and then sort of with high probability, many of these large gates to which the input bits are being fed sort of die off with high probability over the choice of random inputs. And so this sort of like simplifies the circuit, and we can prove lower bounds against it. I'm being a bit vague here because sort of random restrictions deserves maybe its own talk. But this is sort of the method you use to prove lower bounds against AC0. And so, okay, you can use this method to show that AC0 can't compute very sensitive functions, namely that it can't compute parity. However, AC02 can sort of trivially compute this parity function just by what we've seen so far. Okay, so now we can continue on our quest to understand when classical circuit results carry over to this quantum setting. And so you can ask, okay, is there a quantum analog of AC0? And can we show that it can't compute parity? Does this AC0 strictly contained in AC02 result sort of hold in some sort of quantum setting? And so the answer is sure.
Before you go on, I just wanted to quickly check. So NC0 is strictly contained in AC0. Do we know this? Or Is that just the light cone argument again, or?
Yeah, so you can use this light cone argument to show that, for example, like the AND function. So the function that returns 1 if and only if all of the inputs are set to 1.
Right.
This function, is not computable in NC0 by this light cone trick. Yeah.
Sorry, thanks.
Sure. Yeah, any more questions before going on? Okay. Also, if anyone joined late, I can't see you. I'm like stuck on my slides here. So just shout in if you have any questions. Okay, moving on now. Yeah, so this QAC0 versus QAC02 problem has received a lot of attention, but yeah, so as you can see here, we sort of have this graveyard of past attempts at trying to prove the separation holds quantumly. And this is not to disparage any of these works. These are all very fantastic papers that develop some very nice methods for attempting to understand quantum circuits, but they do all fall short of this goal of proving that QAC0 can't compute parity. And yeah, I guess I'll just highlight that in recent years, these works of Rosenthal, Nadim-Pali, Pade, and then finally this most recent work of Anshu have sort of progressively proved stronger and stronger lower bounds, but they're still seemingly quite far away from proving that QAC0 can't compute parity. And so my point of saying this is that this is a very hard problem and won't be the focus of this talk. Yeah, as I mentioned, there are barriers to separation sort of inherent in these prior attempts. In particular, we know that constant depth quantum circuits are quite powerful. This is sort of going back to this Bravi, Gossett, and Koenig line of work. And then there's a follow-up by, I believe, Benny, Watts, Kotari, Schaefer, and Tall, in which they sort of continue showing that there are tasks computable by these constant depth quantum circuits. And they're able to show impossibility results for like increasingly strong models of classical circuits. And so this is sort of taken as evidence as some barrier to proving limitations on quantum circuits. And yeah, another barrier to mention is this sort of interesting connection between Fanout and Parity that I'll discuss shortly. And then finally, I sort of just mentioned a few quick words about this sort of very beautiful classical method of random restrictions. But as far as we can tell, it sort of doesn't seem like sort of any quantum analog of this technique can be made to work. And so, yeah, we're sort of stumped on this problem in terms of showing lower bounds against more powerful models of quantum circuits. And so this sort of leads to the motivation for the work I'm talking about today. This was a lot of lead up, but yeah, sort of the goal of this work is to sort of come at it from the other side is can we show better upper bounds? In particular, can we find other gates, say other than parity, which when our quantum circuits are augmented with them, can they sort of display the same sort of power? Can they compute hard Boolean functions? And so as the title of the talk suggests, the answer is yes, and indeed this mysterious quantum threshold gate, which I will define in a little bit, is indeed powerful. Okay. So yeah, returning to this red asterisk from before, I mentioned that there's like a slight caveat to take note of when sort of trying to define these quantum analogs of what classical circuits are doing. And that is captured by this notion of Fanout. And so, okay, I haven't talked about this yet so far, but in all of the classical circuit classes discussed so far, it's sort of allowed or assumed that for free, one is able to sort of copy the output of any gate in the circuit and feed it into sort of any future gate in the circuit. Meaning that you can have sort of any number of wires outgoing from any gate in your circuit, sort of feeding forward into future gates in the circuit. And so this is what we call Fanout. Even in NC0, while the fan in is constant, the fan out was unbounded. But this sort of didn't stop us from bounding the size of the backwards light cone. But sort of the problem here, or the issue, is that quantumly, it's sort of a bit fickle to define what the analogous thing is. In particular, our circuit needs to be reversible, so we sort of can't have any splicing of wires or anything like that. Our circuit needs to be a unitary, and so we need to define some new unitary, which sort of achieves this sort of fanning out of a bit, and so I'll get to that in a second. Yeah, so if you want to define some quantum analog of what it means to fan out a single bit, then sort of the unitary that you might think to look at is what I've shown here, which I'll call the fan-out unitary from now on, where this unitary acts on n plus 1 qubits. And you can sort of see on the right here, we've decomposed it as like a sequence of C0 gates, which are each controlled on this starting bit, this B, and sort of copied onto each of the other bits that are input into this gate. And so, yeah, this is sort of the quantum analog you might want to try to define if you did want your circuits to sort of have fan out like a classical circuit would. Yeah, once you give your circuit the ability to sort of use fan out, then you can actually sort of simulate NC0 circuits sort of with this fan out ability that we sort of don't a priori include in our definitions of our quantum circuits. Any questions about this? Okay. But as I mentioned, there is sort of a bit of a strange connection between, or rather a surprising connection between this quantum fan-out unitary and actually the unitary that computes parity. And so this was first observed by Moore in this very nice paper from 1999, in which he proves that the class QNC02, so QNC0 with parity gates, is actually equal to QNC0 with these fan-out gates. And what this means is that if you were to augment your QNC0 circuits with this fan-out unitary, then they could compute parity. And so this is a bit surprising, and I'll explain more later. But the proof isn't very hard. So in particular, all you need to do is just conjugate your fan-out unitary by Hadamard's on all qubits, and you sort of exactly recover this parity unitary. But sort of the reason that this is surprising is that in our classical models, we allow for fan-out, even in NC0 and in AC0, but this doesn't give them the ability to compute parity. And nevertheless, yeah, we're able to apply things like random restrictions, and sort of fan-out doesn't get in the way of us proving strong lower bounds against these quantum classes. All right, sorry, against these classical classes. But quantumly, you sort of just automatically get the ability to compute parity if you allow for this sort of fan-out operation. Yeah, and so this is a bit surprising in my opinion. And so, yeah, let me just like briefly sketch how this goes. So here we have the sort of depiction of our fan-out unitary, in which the bottom qubit is sort of being copied onto the first n, and we can conjugate like by Hadamard's, like I mentioned, and then we can sort of apply this like naive decomposition. We can sort of look at this fan-out unitary just as a product of C-naughts, as before. And it turns out there's this nice fact that if you conjugate a single C-naught gate by Hadamard's on both qubits, then the result is still a C-naught gate, but the order of the control and the target qubit is flipped. And so if you sort of multiply by the identity at the right spots in this sort of circuit in the middle, then this is exactly what you end up with for each of these C-naught gates. And so you just flip them around, and now each of these C-naughts is sort of controlled on these like sort of input qubits, and the output is on the last sort of wire here. And you might recognize from earlier that this is the decomposition that I described for this sort of parity unitary, this sort of naive decomposition. I'm only using these decompositions as like for like illustration purposes. But the point is that if you conjugate this Fanout unitary by Hadamard's, you just end up with parity. And so, okay, let's take a step back and maybe return to this like story we were trying to tell earlier, which is which classical separations can we sort of extend to the quantum setting. And so sort of another seminal classical circuit complexity result is that this AC02 class from earlier is strictly contained in TC0. So let me quickly define what TC0 is. So TC0 is the class that, yeah.
Like I have a question. So
sure.
Like what exactly is the reason the Fanout gate is defined as such in the quantum case? Like why do we need to like copy it to like every why do we need to make n copies of the qubit? And wouldn't it just suffice to have like, wouldn't it just suffice if we could copy it into like one ancillary qubit? Like why do we need n C-naughts?
Right. Like the point here is that you could copy a single qubit with a C-naught gate into an ancilla, but the sort of point of this Fanout unitary is trying to give us this excuse me, this ability we had in the classical case, where we were able to take the result of a single gate and fan it out into like any number of other gates in the next layer of the circuit that we wanted. But if we just tried to do this with C-naughts, then sort of as you can see here, you would need like a lot more depth. So the point is that if you tried to implement this Fanout unitary with 1 and 2 qubit gates, you would sort of like almost certainly incur you would certainly incur a blow up in depth. Like you can show that if you tried to implement this Fanout unitary with 1 and 2 qubit gates, the resulting circuit would necessarily have depth log n. Here is that if we wanted this to be accomplished in depth 1, as is the case sort of in our classical NC0 circuits, then sort of this is the natural thing to define. Does that make sense? Okay. Yeah, I guess it is a bit strange to see at first, but the point is we're sort of just trying to mimic, I guess, what's going on in the classical setting, as to say, okay, let's augment our circuit with sort of the analogous ability that we did have when trying to fan out a single bit. Okay. Yeah. So we're now looking at another sort of seminal result in classical circuit complexity, which is regarding this class TC0. So TC0 is this class where we have everything that we have in the AC0 case, which is and OR gates of unbounded fan-in, and we're also augmenting it with the ability to compute majority. In fact, the sort of standard definition allows for any threshold gate, but for simplicity, just imagine it's only majority gates. Yeah, so this is also a constant depth class, but now it's also able to compute this majority function. And
I'm sorry, could you please remind me, you might have mentioned it, I might have missed it, what the definition of a threshold gate is? Like majority is an example, but what is the definition in the general case?
Yeah, majority is an example. Yeah, sort of the precise definition.
Just the idea is enough. Yeah, it's okay.
Oh, sure. Just imagine a gate that checks if the Hamming weight of the inputs is above some threshold. So
okay. Got it.
Yeah, you sum up the input bits and then say, oh, is it greater than some target value k or something like that?
Okay.
Yeah.
Thanks.
Yeah, so in general, those would be the kind of gates that are allowed sort of in the usual definition of TC0. But here, we're only allowing for majority gates, but this sort of distinction actually doesn't matter. But don't worry about that too much.
Majority would be like it looks at more than half the bits are one way.
Yeah.
Okay.
Yeah. Are n over 2 or more of the bits set to 1. Yeah. And I guess in the odd case, it would be like the ceiling of n over 2. Yeah.
Okay,
and
thanks.
Sure. Yeah. And so, okay, the point is that majority is again another sort of like hard Boolean function, and what I mean by that is that even if you, okay, so AC02 is the class that we have on the left here. So AC0 circuits augmented with parity gates. But we know from Razborov and Smolensky from 1987 that AC02 circuits can't compute this majority function. And so, yeah, I won't get into how this is proven, but it's sort of this very nice method of looking at your circuit as a low degree polynomial. And you can show that if you hope to compute majority, even approximately, sort of the resulting object needs to be sort of a high degree polynomial. Yeah, I'm being intentionally vague here, hiding a lot of very nice classical machinery. But yeah, the point is that we even know how to show that AC02 can't compute this majority function. And so we can ask, okay, what about quantumly? Can QAC02 with parity gates, can it or can it not compute this majority function? You know, somewhat counterintuitively, somewhat surprisingly, in contrast with sort of the classical picture, the answer is actually that QAC02 can compute majority. It can compute any threshold function. And the A here actually doesn't even matter. QNC0 augmented with parity gates can even compute majority and other threshold functions. And so this was a result of Høyer and Špalek from 2005 in a paper entitled Quantum Fanout is Powerful. And so, yeah, you might be able to guess that the title of our paper is inspired by their work. Yeah, so the point here is that if you augment your quantum circuits with this parity gate or equivalently with this fanout gate, then resulting circuit class is extremely powerful, able to compute you know, not only parity but also these threshold functions. And so, yeah, now I guess I'll sort of show a picture here of sort of the classical picture versus quantum, sort of in terms of what we know. And so in these diagrams, the solid lines represent inclusions that we have proven are strict, meaning there is a function, for example, on the left here in AC0 that isn't in NC0, and so on. But on the right here, the picture is quite different. The dashed lines represent inclusions that we don't know to be strict. So the one that I just mentioned is that QNC02, which is equal to QNC0 with fanout, which I haven't shown here, is also equal to QAC02, can compute majority and can compute other threshold functions, which means that with these circuits, we can actually just simulate sort of these quantum threshold circuits. Which I haven't explicitly defined yet, but hopefully that makes sense. And moreover, there's another dash line here, which is that we don't know if QAC0 can compute all the functions that QTC0 can. I guess, yeah, another thing I'll point out here is that augmenting our quantum circuits with fanout sort of makes them extremely powerful, bringing them to the very top of this sort of inclusion lattice. But classically, the ability to compute parity, sort of if we just gave that to our NC0 circuits, well, it doesn't actually result in all that much power. We have this strange class NC02 here, which is sort of near the bottom. It's still not very powerful. Like I mentioned earlier, it can't compute the AND function. Another sort of strange thing to observe here is that TC0 sits at the top of this sort of classical hierarchy, but quantumly we don't know whether or not the resulting class is actually sort of at the top, can sort of simulate all of these other models. or can compute some function that these other restricted classes can't. And so the point of our work is that we make, I guess the sort of tagline is that we make the picture on the right a little less strange, in that our sort of main result is that QTC0 contains QNC0 2, or QNC0 with Fanout. And so the rest of the talk will be devoted to proving this. And one caveat is that the resulting construction yields some amount of approximation error, but this is up to some like inverse polynomial. So what I mean by this is that, say with probability 1 minus 1 over n, we construct a circuit that can compute the parity function. We construct a QTC0 circuit, which with probability 1 minus 1 over n can compute parity, and therefore can approximately simulate these QNC02 circuits. But yeah, one thing to note is that this Høyer and Špalek construction also achieves a similar inverse polynomial approximation error. And you know, moreover, a lot of the time, sort of in quantum computing, we really only care about computing things approximately, sort of with bounded error. So I don't think this is too much of a caveat. But this construction of Høyer and Špalek was actually made exact, meaning there is a circuit which incurs no approximation error, and this is a result of Takahashi and Tani from 2011. And sort of one bonus, maybe to cancel out the caveat, is that our construction applies to sort of a more general set of gates than just threshold gates or majority. And this is sort of in contrast with the classical setting. Sort of the objects we define don't really seem to be classically interesting, but they sort of paint an interesting picture of these sort of generalized majority or generalized threshold gates. And I'll get into that later. So any questions before we go on?
So sorry, just a quick clarification. So you mentioned in the previous slide, did I understand it correctly that we are saying that QTC0 is contained in QNC02?
Yeah, exactly.
That? And now you're showing the converse, is it?
Yeah.
So they're equal. Yeah. So like we have a full characterization from your
exactly.
side. Okay. Yeah. Okay. Wow. Okay. Thanks.
Yeah, sure. Yeah, the containment QTC0 in QNC02, this was first proven by Høyer and Špalek, because they give a construction that uses one of these QNC02 circuits to compute majority, and then from there you can simulate. Yeah, exactly.
Right. So threshold is as powerful as Fanout, essentially. That is the
yeah. Yeah, that's exactly right. Yeah. Okay, great. Yeah, so I will spend the rest of this talk showing how to prove this inclusion. So sort of like the first thing you might ask, maybe if you're like well acquainted with the sort of like classical circuit complexity tricks, is why isn't this result just trivial? Like why we have this nice classical picture where TC0 sits on top. Why is it not the case that this sort of quantum thing doesn't hold? In particular, we know that threshold gates can be used to simulate parity classically. I mean, like you can actually do quite a bit more, but we at least know this. So let me sketch this. So I'm going to define this type of Boolean function called an exact threshold function. And so here, I've denoted this as exact k of x. Exact k just checks whether or not the Hamming weight of the input x is exactly equal to k. And so if the Hamming weight is exactly equal to k, the function evaluates to 1, and otherwise it evaluates to 0. And so the first sort of thing you can observe is that to compute this function, you could first check threshold k of x, which here I mean, is the Hamming weight of x at least k? and this other function, not threshold k plus 1 of x, is the Hamming weight of x sort of strictly less than k plus 1. And so if both of these evaluate to true, then they're, the conjunction of these two should give us the, the evaluation of exact k on x. And so, okay, so what I've on the slides here now is a TC0 circuit, this exact k function, sort of as I just described, and by this like formula in the box here, can be computed in TC0, sort of for any k, let's say between like 1 and n. And so you can sort of assume that that's for free. And so in this TC0 circuit, what we have is this exact 1 gate, this exact 3 gate, 5, so on, all the way up to n. Here, let's assume n is odd. And so what this circuit is computing is we're checking explicitly if the Hamming weight is 1, 3, ... for all these odd values up to n. And if any of these gates evaluates to 1, then we know that the input string must have had an odd Hamming weight. And so taking an OR over all of them should tell us whether or not the parity of the string is 0 or 1. And so like I said earlier, you might be tempted to ask, why isn't this result trivial? We can simulate parity in TC0, sort of by the circuit I've drawn here. But you have to be quite careful here because this circuit has a large fan out. So if you actually wanted to go and implement this circuit, the resulting fan out on every single input bit would be super constant. Actually, it would be n here, n over 2, omega then, let's say. And so the point is that it sort of seems like you might not be able to actually simulate this with a low fan out. In fact, I think there are some works, in particular, I think there's a work of Daniel Kane and Ryan Williams in which they show that threshold circuits with a bounded number of wires, so sort of some proxy for fan out, can't approximate the parity function very well. Yeah, and so the point is here, you sort of critically need to rely on fan out in order to compute parity in this way. And quantumly, we don't assume that we have the ability to compute fan out. So if you wanted to, do a similar thing on your QTC0 circuit, it just wouldn't work. And okay, so what I'm going to describe now is how to show this inclusion sort of without going through this like naive classical picture. In particular, we're going to show how to implement this fan-out unitary. And to do so, we're going to follow along a similar proof outline to a result of Greg Rosenthal in 2020, where he shows that a particular state preparation task actually suffices for implementing fan-out. And so actually what I will focus on is how to achieve a similar state preparation in QTC0. And via Rosenthal 20, this suffices for implementing fan-out or parity. Okay. So the state preparation task I'm talking about is preparing what's called a cat state. And so in the middle of this theorem here, this is just the state, which is an even superposition between this all zeros string and this all one string. And so in this work of Moore from 1999, he shows that if you can implement some unitary U and its inverse U dagger, where U satisfies U applied to the all zeros input yields this cat state, then it turns out that in conjunction with OR gates, you can build a circuit sort of just consisting of U dagger, and OR that computes parity. And so that's sort of what I mean by an equivalent state preparation task. Yeah, so I will get into this now. Is the statement of the theorem clear? Are there any questions? Okay, I'll go on. Yeah, so the sort of circuit construction, I guess, that yields this equivalence between this task of computing the parity function And the state preparation task is pretty simple. It's as follows. We have our input bits, x1 through xn, on these first n wires. And then on n ancillary qubits, we have our unitary U, which prepares the cat state. And finally, we have this single bit B on our final wire here. And so after this unitary U is applied to the ancillas, which are initially set to all 0, the resulting state is sort of just X tensor this cat state, tensor this final bit B. And then in the next layer, we're going to apply a controlled Z gate. So this is just a gate that maps 1, 1 to minus 1, 1, and then does nothing to any of the other computational basis states. So this is a 2-qubit unitary. And we're applying it between the first bit of X and the first bit of this cat state, and then the second bit of X and the second bit of this cat state, and so on, for all n input bits. And the point is that none of these controlled Z gates are overlapping, so we can implement them in a single layer of our circuit. And so after all these controlled Z gates are applied, you can just pretty easily compute what the resulting state on all these registers will be. In particular, because of how the controlled Z unitary works, you pick up a -1 phase sort of only on this like one component of the cat state, this like 1 to the n component. And you pick up this -1 phase every time a bit of X is set to 1. And so the total number of phases you end up picking up is just equal to the Hamming weight of the input string X. And what this means is that if the input string had Hamming weight which was even, i.e. Even parity, then nothing happened. The state is as it was. But if the input string had odd Hamming weight, then we pick up a -1 phase on the second component of the state, and we sort of have this like minus cat state. Right. And so then we apply U dagger on the ancillary qubits, which are sort of in one of these two states, depending on the Hamming weight of X. And so this is sort of where the magic happens in this construction. When you apply U dagger to the sort of minus version, the version of the cat state where we have this -1 phase on this all ones component, then the result will be orthogonal to the basis state of all zeros. And the reason for this is that when you apply when you apply U to all zeros, you get the cat state, but U is unitary, in particular it preserves inner products. And this sort of minus version of the cat state is orthogonal to the cat state. When you compute this inner product, the result is 0. So when you apply U dagger to this minus version of the cat state, the result is going to be orthogonal to the all zeros computational basis state, meaning that it's only supported on strings that have a 1 in them somewhere. And so when you apply this OR gate, you'll find that, so this is what I've just mentioned. When you apply an OR gate, it will sort of fire with certainty, because all of the sort of components of the state we have now all have a 1 in them, meaning this OR function always evaluates to 1 for each of these possible inputs which are in superposition. And so we always flip this B qubit. However, if the Hamming weight was even, if the Hamming weight of X was even, then applying U dagger returns this state to all zeros. Because remember, U applied to all zeros is the cat state. Applying U dagger takes us back to all zeros. So this OR gate will not fire because we identically have 0 on these ancilla qubits. And so, so the point is that in either case, we will have correctly computed the parity of X. So that was a lot. I'll pause for questions for a second. So yeah, here's the theorem statement again, which just says that if you can implement such a U and U dagger in constant depth, then all you need is an OR gate, and now you can compute parity. And so this is the sense in which I mean the state preparation task and computing parity are equivalent. But sort of one extension of this was first observed by Rosenthal in this paper from 2020, in which he shows that a slightly weaker state preparation task actually suffices for computing parity. And so what I've shown here is this this state, which Rosenthal calls a Nekomata state, which in some sense can be thought of like a dirty cat state, wherein the state that we're hoping to prepare sort of only needs to look like a cat state on the first n qubits. So here, psi 0 and psi 1 are some arbitrary states on, let's say, like a ancilla qubits. And so what Rosenthal showed is that if you can prepare a state like this for some arbitrary psi 0 and psi 1, then this actually also suffices to compute parity. And sort of the reason for this is that if you were to run through the construction that we just went through with this U now acting as shown here, instead of as actually preparing an n qubit cat state, if it prepares this seemingly weaker Nekomata state that has some junk qubits hanging off the end, then it turns out this actually suffices to compute parity. Further, he shows that if you can approximately prepare one of these states, say just prepare some state that has high fidelity with such a Nekomata state, then you can actually still approximately compute parity, and the precision of your approximation is going to be essentially the same as the fidelity between the state you prepare and sort of the ideal state you would have hoped to prepare. Okay. And I should just also mention that in this work of Rosenthal, he gives a construction, a QAC0 construction, a circuit which prepares an approximate Nekomata with inverse exponential approximation error. But the sort of trade-off is that the number of ancilla used is exponential in n. And this is sort of interesting because prior to this work, it was unknown if QAC0 circuits of any size could compute the parity function. Right, as I mentioned, preparing a Nekomata is equivalent to preparing a cat state, and then as we saw from this circuit just a few slides ago, this suffices to compute parity or Fanout. And so the point is that the analogous sort of classical question of is there an AC0 circuit of any size which computes parity? Well, this is a pretty easy question to answer because for any function you can write out sort of a CNF for it, which might be exponential size, but you can always implement such an exponential size circuit that like exactly simulates this CNF formula for any given function. But quantumly, we didn't know if such a thing was possible. And sort of in this very nice work of Rosenthal, he shows that by very different means from the classical setting, you actually are able to, with a QAC0 circuit of exponential size, compute this parity function.
And the classical construction we can't directly apply because that would involve Fanout, right?
Yeah, exactly.
What you're describing.
Exactly.
Okay.
Yeah, like generically, variables would participate in like many, potentially exponentially many clauses. Yeah. And so we need some sort of like new sort of like inherently quantum tools in order to like achieve the same thing. And so I'll now get into how Rosenthal proves this and how our construction sort of makes use of similar ideas. And so the sort of key idea from Rosenthal's construction is that in parallel, one can prepare many sort of bad cat states, bad but not horrible, I've written here, and then again in constant depth can boost the entanglement of these quote unquote bad cat states to achieve a good Nekomata state. And so what do I mean by bad but not horrible here? The bad part is that these sort of approximate cat states that one can prepare in constant depth have very bad fidelity with the cat state, meaning barely above a half, right? Because sort of the all zeros computational basis state already has fidelity a half with the cat state, but that's not exactly what I mean here. These states have, let's say, like fidelity a half plus epsilon with the true cat state for some very small epsilon. But I say not horrible because these states I'm talking about have sort of the right distribution on measurement outcomes if you were to measure them. Meaning that if you were to measure one of these bad cat states, the sort of overwhelming measurement outcomes you would see with very, very high probability would either be all zeros or all ones. Now, it might be the case that all zeros sort of happens with probability very close to 1, but sort of the next most likely outcome would be all zeros, or all ones or all zeros. I can't remember which order I said them in, but yeah, I've sort of depicted this here with this histogram showing like what the sort of likely measurement outcomes would be. Yeah, and so like I said, it would be the case that with probability very close to 1, you either measure all zeros or all ones. Sort of most of the mass of the state is like in the right place, but like very lopsided, as shown here, with the all zeros probability being much less than the all ones probability, and then some very like negligible probability of observing anything other than these two like very special basis states. Yeah. Okay. And so, okay, let's remember these Nekomata states are sort of the goal for what we're trying to achieve here with our constant depth circuit. And so these are states where the first n qubit sort of looks like the cat state, sort of has exactly the right measurement outcome if we were to just zoom in on these first n qubits. And then on some other number of qubits, we sort of don't care what happens. It's just some other arbitrary state psi 0 and psi 1. And so, okay, what is our circuit going to do? It's going to act on sort of this n by m plus 1 grid of qubits. And as you can see here, the first column is sort of pulled away from the rest. And these n qubits are going to be the sort of good n qubits, which sort of act like the cat state. And then the rest of the grid is going to be sort of the junk, psi 0, psi 1, that we don't really care what's happening there. All we want to ensure is that these n qubits furthest to the left, when we measure them, sort of have exactly the same distribution as the cat state would. Yeah, as I mentioned, these target qubits should either be all zeros or all ones, and then these ancilla qubits, we don't care what happens. Okay. Now, for each, so the construction proceeds as follows. For each column of this sort of ancilla grid, we're going to prepare one of these bad cat states that I just mentioned from before, which sort of have this very lopsided histogram with the mass in the right place on all zeros and all ones, as you can see here. And then what we're going to do is we're going to ensure that m is sort of the right value such that the following event occurs, such that either all of the columns are all ones with probability about a half. So as you can see here, this bar on all ones in the plot here is very large. It's very close to 1. But we can pick m large enough so that the probability of observing all ones in every column, if we were to measure this whole state, would be roughly a half. And so sort of why is this a desirable thing to do? This is good for us because if any column isn't, and if we measure this whole grid of qubits and any column's measurement outcome isn't all ones, then the next most likely thing for it to be is all zeros, meaning we'll have a column of all zeros. And so why is this good? This is good because what we're finally going to do is apply an AND gate sort of across each row, with the output qubit being on this like target column. And so what does this mean? What's going to happen, I guess, in these sort of scenarios I've sketched thus far? This means that if the whole grid is sort of measured as all ones, applying this AND gate is going to put a 1 on every qubit in this target column. But if any column is all zeros, then none of the AND gates are going to do anything, meaning that the target column is going to remain all zeros. And so this is sort of what I meant in the previous slide about like boosting the entanglement of these bad cat states in constant depth. So I'll pause here because yeah, this is a bit complicated, I guess.
I do want to ask some questions, but we only have about 10 minutes, so I don't know. I don't know how many more slides you have.
Not too many more.
Okay. Right. So for each column on the ancilla qubits, I'm producing. Oh, I think I got confused. I thought we were producing the. Okay. So on each column of the ancilla qubits, we are preparing that this state, right, which has this distribution that you've drawn. And then you're saying that if you have m large enough, then it would be the case that measuring all ones in ancillas would happen probability half. So I measure a column, probability happens with probability half.
I'm saying here that if you measured all of the columns, they would all be all 1 with probability a half. You can sort of think of this each of the columns as like a biased coin, which is like biased to all ones.
Yeah. That makes sense. Yeah. So larger than, more unlikely it would be that they would all turn up 1. And of course it's a So you can get to that point. Yeah. Okay.
But then sort of the key thing is that if you don't get all 1s, you have
then
all
the
zeros.
Next most likely thing is all zeros. Okay, so that's good. And then let's say for each row apply AND gate from because you're doing the all ones, you're testing them and then accordingly you're storing them. Makes sense.
Yeah.
Okay, thanks.
Yep. Sure. Okay, and then here's just like a quick visual depiction of that. All 1s, get all 1s, but then if some column is all zeros, every every target qubit will remain 0. So now I'll just like briefly mention sort of this thing I said earlier about like a generalization of majority gates. And by that I mean gates that sort of are only like sensitive to the parity of the string they're acting on. So we'll let S be some subset of bit strings that all have the same parity. And we'll define this US gate as some gate which just adds a phase depending on whether or not X is a member of that set S. And so, for example, if S was the set of all odd bit strings, then US would sort of like be computing the parity in the phase. But we don't, in general, require for that to be the case. And so remember what I said earlier, which is that threshold gates can be used to generate these exact threshold gates. And it turns out that these exact threshold gates sort of fit this criteria of this thing I've just defined. They are parity restricted, in particular because all of the strings have the same Hamming weight. So of course they're all going to have the same parity. And the size is going to be about n choose k. And so it turns out that parity restricted gates sort of serve as like a natural generalization of sort of the feature we're interested in the sense that they like weakly approximate parity. So I'll denote ds as like the density of one of these parity restricted sets, which is just the size of the set divided by 2 to the n minus 1. Okay. And okay, don't worry too much about the circuit I've drawn here. This is the circuit in our construction, and this is the circuit we use to generate these like bad cat states. And it turns out that if you have some parity restricted gate, one of these US gates, then you can show that the probability of measuring all zeros when you construct a state as shown above sort of only depends on the density ds. And it turns out that this density is sort of the only relevant thing for getting like a measurement distribution that's desirable, like these histograms I keep showing. And so it's, yeah, not too important what the quantitative thing here is, but this like weakly approximating parity thing lets you get some sort of measurement distribution that's desirable. Okay, so I'll run through the construction one final time. We want to pick M large enough so that the probability that measuring all of the columns as all ones is about a half. And it turns out that if M is about 4 over the density squared, then this probability is indeed very close to a half. And then a similar calculation reveals that the probability of all 0 is also very close to a half. Yeah, both of these quantities sort of only depend on this density I've mentioned earlier. But sort of the relevant thing is that if you go back to these exact threshold gates, which are examples of these like parity restricted gates I was mentioning earlier, then this density is just equal to n choose n over 2 divided by 2 to the n, which is about 1 over root n. And so you end up getting inverse polynomial precision, meaning that when you apply these AND gates horizontally, sort of the state you get is one of these approximate nekomatas, and the approximation factor is inverse polynomial in N. Yeah. And so here it all is again one more time. You prepare these bad cat states, and then boost the entanglement with these large AND gates onto the blue qubits, which are the targets here. And so, yeah, here's the theorem statement one more time, sort of stated in more general terms, which is that if you have one of these US gates and AND gates, then you can construct a constant depth circuit that approximates the parity function, and the size of the circuit is going to be polynomial in n and 1 over the density of the set. And in particular, this gives us a polynomial-size threshold circuit for parity, and gives us our inclusion via the equivalence as stated earlier. And I guess I'll just briefly mention that if your parity restricted set has size 1, this is sort of equivalent to an AND gate, and this like directly generalizes the exponential size construction of Rosenthal with a similar size and approximation guarantee. Okay, so I'm just about out of time here, so I'll just conclude with a few open questions. One is whether or not the construction we give can be made exact. So this would be analogous to what Takahashi and Tani showed. Another is sort of the big open question, which is, okay, not threshold gates, but what if you only have AND gates? Can we say anything there? Can we prove lower bounds? And a third question is, which of these threshold functions are computable in QAC0? We have a good answer for AC0 for the sort of analogous Boolean functions, but we sort of don't really know anything about what's going on in QAC0. And then finally, is there a complete characterization of which Boolean functions are powerful in constant depth? So sort of beyond this like parity restricted notion we introduced. And then on the right here, we have sort of the updated inclusion lattice now with QTC0 on the top.